Video 5-2, continuing on with periodic trends and also looking at electron configurations for transition metal ions. Okay, so a couple more periodic trends we want to look at. Next one is called electronegativity, and be careful. Okay, the other one, electron affinity, sounded similar to it. Okay, electronegativity. This measures the ability of an atom to attract electrons toward itself when it is chemically bonded to another atom. So in other words, it's in a chemical compound. Okay. Now, the general trend. Okay, so basically we're saying you have one atom here and one atom here. Okay, and they're going to bond to each other. Now, each nucleus is going to be pulling on the shared electrons. So how strong is the pull between atom A and atom B on these electrons right here? Okay. Well, general trend again. Go back to the atomic radius. Which one is going to pull stronger on the atoms? Big atoms or small atoms? Okay. As we go left to right, the electronegativity increases. The smaller the atom is, okay, the stronger the nucleus is going to be attracted to its own electrons plus the ones that are being shared by the electrons there, or by the two atoms. Okay. And when you go down, because the atoms get larger, the electronegativity will decrease. Okay, so which of these will have the largest electronegativity? Okay, again, find these on the periodic table, pause, and then come back and check your answer. Okay, answer is fluorine. Okay, ignore all this stuff here. Okay, now, you may say, well, isn't helium smaller than fluorine? Aren't we looking for the smallest atom? Okay. Yeah, it is smaller, but remember, electronegativity deals with bonding. Okay. How strong will the atoms pull on electrons when it bonds? Helium doesn't bond, so it's the one with the largest electronegativity is fluorine. Okay. Noble gases basically have no electronegativity to them. Okay. Now, ionic radii. Okay. What is the radius of an ion? Okay. Now, remember this. Cations will always be smaller than the atom that they came from. Okay. Why is that? Well, when it's a cation, it has to lose electrons. Now, that makes the attraction between the nucleus and the remaining electrons stronger. Okay. And also, what happens when you go from lithium to lithium ion, lithium plus 1? Well, lithium had two rows of electrons, two energy levels. Lithium ion, because that last energy level only had one electron in it, it went away. So now you only have one energy level of electrons. Okay, so you lose a whole energy level. So naturally the atom, the ion is going to be a lot smaller. Okay, anions, because you're adding electrons, will always be larger than their neutral atoms. Okay, so what's the trend? Well, take a look. As you go left to right, row 2, row 3, row 4, row 5, the ions tend to get smaller. Okay, and same for the anions. As you go left to right, they get smaller. Not by a lot, but if you look at the actual numbers, you notice they are getting smaller. Okay, now be careful. These are in the same row. These are way larger than these. Okay, so the general trend, as you go left to right, they get smaller, but the smallest is not on the right side. The smallest will be here. And the largest ions are not going to be on the left side. The largest will be here. Okay, in the middle, basically. The smallest would be in like the +3 column, and the largest would be in the -3 columns. Okay, and when you go down, they get larger. Why? Even though these are still cations, this still has one more energy level than this one up here. The potassium still has one more energy level than the one above it. Okay, now, what if they're in different periods? Okay, well, if you're going to compare ions from different periods, the cations are usually going to be smaller. Doesn't matter where they're located, if how far up and how far down one is. Okay. Look at the electron energy levels of the ions. Okay. The cation might actually be larger if the difference in energy levels between where the anion is and the cation is greater than 3 energy levels. Okay. If the electron energy levels are the same. So, if you notice here, the sodium ion, even though it's in row 3, only has 2 energy levels. The fluoride ion is in row 2. So this, also has 2 energy levels, not 2 electrons. Okay. So, which one's going to be smaller? Well, simple. These two are isoelectronic. They have the same number of electrons. So, the larger one is going to, or the larger atomic number will be the smaller ion. Why? This has more protons. The sodium has more protons than fluorine. Okay. Now, which of these will be the smallest radius? Again, find these on your periodic table and take your guess and come back. Okay, smallest one is magnesium. Why? These are all isoelectronic with each other, but this has the most protons. Okay. Again, which one of these will be the largest radius? Okay. Correct answer, oxide ion. Why? Again, they're all isoelectronic. This has the least number of protons. Okay, last thing we'll look at, electron configurations for transition metal ions. Okay, all transition metal ions are formed by losing their electrons first from the s orbitals. Okay, in other words, here's the configuration for zinc. Okay, the noble gas configuration, argon 4s2 3d10. Okay, now the zinc ion, you should have this memorized as to what charge it's going to be. Zinc turns into the +2 ion. Okay, so +2 basically means we got to lose 2 electrons. Okay, so normally we'd say, well, the 3d is higher than the 4s, so they must be coming out of that, out of the 3d. Okay, but the configuration is not 4s2 3d8. The configuration is argon 3d10. Okay, we lose them out of the 4s orbital first. Okay, so which of these is the correct configuration for Fe3+, the ferric ion? Okay, pause it, figure out the configuration for iron first, and then +3 means remove 3 electrons from it. Okay, the correct configuration is this one right here. Okay, this is just normal Fe right here. Okay, so when I take out 3, we don't take them out of this D6 first. We have to first remove them from here first, and then you remove any extras that you need from there. So get rid of those and remove one more, and you end up with just simply 3d5. And now your review. Okay, where on the periodic table should you find the element with the largest ionic radius?